In this video, we're jumping into chapter 6, and we're going to be talking about solving systems of equations. Starting off with section 6.1, we're going to be looking at systems of linear equations, or you could say systems of equations with unique solutions. So let's start with a system of equations that looks like this, and we're going to figure out how to rewrite this in matrix form. So what we're going to do is we're going to create a rectangular array of numbers that looks like this, called a matrix, and that's just going to store the information from our system. So the columns here are going to represent our different variables, x and y. The vertical bar here is going to represent the equal signs, and over on the right sides we're going to write the numbers for each equation. So the top equation here, 3x plus 6y equals 30, if we put that into matrix form, we're just going to pull out the coefficients. So we're going to write 3, 6, and then 30. For the bottom equation here, doing a similar kind of thing, just pull out the coefficients, 2, 8, and 32. So writing the system in matrix form, it's much more concise, a lot less writing required, and then this is going to lead us to an efficient way of solving the system of equations. So now that we've got our system in matrix form, there are 3 elementary row operations that we can perform on this matrix to help us find the solution to the system. So here are the 3 things that we're allowed to do. We're allowed to swap 2 rows, so meaning just write the rows in a different order. We're allowed to multiply or divide a row by any non-zero number. So we can divide a row by 2, for example. And then third operation is slightly more complicated. We can do something like current row minus a number times our pivot row. And this particular operation will probably make a bit more sense when we jump into an example. So the goal with doing these 3 types of operations is we're aiming to get a matrix that's in diagonal form. So if we're talking about a matrix with 2 rows and 2 columns, diagonal form would look like this. You'd have 1s along the main diagonal from the top left to the bottom right. You'd have 0s everywhere else. Or if we were talking about a matrix with 3 rows and 3 columns, again, we would see the 1s along this main diagonal from the top left to the bottom right, and 0s everywhere else. And the reason why you're trying to get this diagonal form is because once you get your matrix into this form, it's easy to read off the solution. So the diagonal form is what we're aiming for with these row operations. So let's try to solve the following system of equations. First thing we're going to do is we're going to write this down in matrix form, just like we did before. So the columns are going to represent our different variables. The vertical bar here represents our equal signs, and then over on the right side, we're going to write down our numbers. And we're just pulling the coefficients out of the system. So we'd have 3, 6, 30, 2, 8, and 32. All right, so now we're going to use those 3 row operations that we just talked about to try to create a diagonal form in our matrix. So let's walk through which operations to do in which order. Well, the first thing you want to do is you want to get a 1 in the upper left, and that 1 is going to be called the pivot. So that's our goal here, is to create a 1 in this position here. And the way you're going to create a 1 is you're just going to divide the row by an appropriate number. So if we take row 1 and we divide by 3, that's going to create the 1 for us. Okay, so let's look back at our previous matrix. Divide each of these numbers here in the top row by 3, and you'd have 1, 2, and 10. So that has created our 1 for us, otherwise known as the pivot. Bottom row is not changing, so we're just going to recopy that. Now, once you've got a 1, what you want to do is get 0s in the rest of that column. So let's get 0s in the rest of column 1. There's only one other position in column 1, and it's this position in the bottom left here. So we want to create a 0 in that position. So let's think about what operation is going to create that 0 for us. That's where we want to do the operation current row minus a number times our pivot row. So current row is whatever row we're in, that is row 2. And we're going to subtract off a number times our pivot row being the row that has the 1 in it. So that would be row 1. The number that you want to subtract off is just the number that you're trying to eliminate. So if it's a 2 in that position that you're trying to turn into a 0, you're going to go row 2 minus 2 times row 1. So we're going to do things like 2 minus 2 is 0, 8 minus 4 is 4, 32 minus 20 is 12. So we're just doing that operation row 2 minus 2 times row 1 all the way across that row. So anytime you want to create a 0 in a certain position in the matrix, think about doing current row minus the number times the pivot row, where the number is the number that you're trying to turn into a 0. So top row will just get recopied here. Nothing's changing there. And I'm going to keep this 1 circled, keep the pivot circled. So now that that first column is cleaned up, we are going to move down and to the right, and that's going to be the location of our pivot for the next step. So for our next step here, we want to get a 1. We're doing that now in the bottom right position where the 4 is. And the way you get a 1 is you take that row and you divide it through by an appropriate number. So since it's a 4, we want to turn it into a 1. We'll take row 2 and divide by 4. So that's going to give us 0, 1, 3, and we can just circle that 1, or you could call it the pivot, circle the pivot. Top row can get recopied there. So now that we've got a 1 in column 2, we're going to get zeros in the rest of column 2. So where we're seeing this 2 at the top right of the matrix, that's where we want to create a 0. And the way that you create a 0, you go current row minus the number that you're trying to get rid of times your pivot row. So let's think about this. Current row is the row that the 2 is in, so that's row 1. Pivot row is the row that has the 1 in it in that column. So that would be row 2, because our pivot, let's highlight it, there's our pivot for column 2. Pivot is in the second row, so row 2. The number that we're trying to turn into a 0 is a 2, so we're going to go row 1 minus 2, row 2. In general, current row minus the number times the pivot row. So let's try this operation all the way across our matrix. Row 1 minus 2, row 2, just looking back at our previous step to look at our numbers. 1 minus 0 is 1, 2 minus 2 is 0, and then 10 minus 6 is 4. So that's how we get our top row there. And we can recopy our bottom row because nothing's changing there. So notice the flow of the problem. If we just go back over our goal for each step, what did we do? Well, we got a 1, and then we got zeros in the rest of that column. And then we got our next pivot, our next one, and then after that we got zeros in the rest of column 2. So this is going to become a really familiar process where we just switch back and forth between getting a 1, getting zeros, getting a 1, getting zeros. And that's the rhythm of these problems. So notice that we've now created that diagonal form where we've got 1s along the main diagonal here and zeros everywhere else. And that means that we're ready to just read off our solution. So let's remember what the columns represented here. This was the X column, the Y column, and the number column. And so if we read off the top row of this matrix, that's saying 1 times X plus 0 times Y equals 4. And really, that's a long-winded way of saying something much simpler. 1 times X is the same thing as X, and 0, Y is just 0. So really, that top row is just saying X equals 4. And the bottom row is saying 0 times X plus 1 times Y equals 3. Okay, well, if we write that in a less long-winded way, 0 times X is just 0, and 1 times Y is just Y. So really, bottom row is just telling us the value of Y. So in other words, once you get the diagonal form, you're able to just read off the solution. The solution is X is 4, y is 3. Often what we'll do is we'll write our final answer just as an ordered pair like this. So x comma y, 4 comma 3. So those are the values that solve the system of equations. And this process that we went through of getting a 1 and then getting zeros in the rest of that column, that process has a specific name. It's called Gauss-Jordan Elimination. So when you're doing your suggested homework, the question will say something like, solve using Gauss-Jordan elimination. And then you'll know that means, okay, write up the system in terms of a matrix and then do these sorts of row operations. So in our next section, we'll see that sometimes a system can have no solution, or sometimes a system can have infinitely many solutions. But in this section, we're just sticking with the basic type of system where you get a nice unique solution, meaning you've got a specific value of x and a specific value of y that solves the system. So let's try another example of solving a system using Gauss-Jordan elimination. So we're going to set up the system in matrix form. This time we have 3 variables, x, y, z. We've got our equal signs. We're going to put our constants over on the right side, and we'll just pull out the coefficients from each of these equations. So we'd have -1, 1. The first equation doesn't have any z's in it, so that's 0z is equal to -1. For the second equation, it would be 1, 0, 1, and then a 4. And for the third equation, 6, -3, 2, and 10. So that gives us a way of writing down this system much more concisely. So we're going to go through this familiar pattern of getting a 1, otherwise known as the pivot. We're going to get that in the upper left of the matrix, and then once we've got that, we're going to get zeros in the rest of column 1. So those will be our first 2 steps. So let's think about how to get a 1 in the upper left position. The standard way to do it is just to take our row and divide through by an appropriate number. So you could go row 1 divided by -1. But in this case, there's actually a slicker way to do it, which is to swap 2 rows. So we could just swap row 1 and row 2. And the reason that will work well here is because you notice row 2 has a 1 in the first position. So it would be easy enough just to grab that entire second row, the 1, 0, 1, and 4, and just bring it to the top. And then just bring the entire first row into the middle. The reason that's nice is because there was no algebra required. And then bottom row will just get recopied. So you don't do row swaps all that often, but occasionally you'll notice an opportunity where, hey, it's easier to just swap rows than to divide through by something. So I usually get in the habit of just circling that pivot. And now that we've got that, we're going to get zeros in the rest of column 1. So meaning we want to get a 0 in this position here and this position here. So the way that you get zeros is you think about going current row minus a number times your pivot row, where this number here is whatever number you're trying to get rid of. So let's look at this second row here. What row are we in? Well, that's row 2. What number are we trying to get rid of? It's a -1. So if we go minus -1, that actually becomes a +1 times our pivot row. So the correct thing to do is row 2 plus row 1. And if you look back at our previous matrix, yeah, that'll work. When we add -1 and 1, that is going to create a 0 for us. So this just turns out to be the correct operation to create a 0. We can get the 0 in the bottom left at the same time. So now we're in row 3. The number we're trying to get rid of is a 6. So we're going to go -6 times our pivot row. That'll just be the perfect operation to create a 0 because we'll be going 6 minus 6 to give us a 0. So let's deal with one row at a time. We'll just recopy the top row. Nothing is changing there. And then let's focus on doing this operation row 2 plus row 1. So look back at your previous matrix and just add row 2 and row 1 together. To have -1 plus 1 is a 0. you'd have a 1 plus a 0 is a 1, a 0 plus a 1 is a 1, and a negative 1 plus a 4 is a 3. So that's that row dealt with. And then for the bottom row, we're going to do the operation row 3 minus 6, row 1. Okay, so 6 minus 6 gives us this 0 here. Negative 3 minus 0 gives us a negative 3. 2 minus 6 gives us a negative 4. And then 10 minus 24 gives us minus 14. So that's how we get that bottom row there. So notice we went through that pattern of getting the pivot and then getting zeros in the rest of that column. And we're going to continue that process as we go through our other columns. So once you're done with your column, move from your current pivot, move down and to the right. And this guy is going to be the pivot for the next column. Because remember, what we're aiming for is that diagonal form that has ones along the diagonal. So you're looking for your pivots to be sitting along that diagonal there. So this looks like it's going to work out pretty nicely because happily we've already got a 1 in the center position in the matrix. That's just sort of a fluke that we didn't have to do any extra algebra there. So that's already good. So I'll write get a 1 and I'll just write a check mark since that's already done. And so then we're moving into getting zeros in the rest of column 2. Okay, so let's think about what we're going to have to do. It's that negative 3 at the bottom of the matrix that we want to turn into a 0. And the way you do that is you go current row minus your number times your pivot row, where the number is just whatever number you're trying to turn into a 0. So our current row, the row that we're in, is row 3. Our pivot row is row 2 because that's where our pivot is for column 2. The pivot is in row 2. And the number that we're trying to eliminate is a negative 3. We have to do a sign change and say that's plus 3 times our pivot row. So row 3 plus 3 row 2 will be the perfect operation to do. So let's look back at our previous matrix and do that. So we're going to go 0 plus 0 is 0. Negative 3 plus 3 is a 0. Negative 4 plus 3 is a negative 1. And then negative 14 plus 9 is a negative 5. So that's how we build up that bottom row. And the other 2 rows can just get recopied at this point. So now we're really in the home stretch, because if we think about what else we have to do, well, we just have to create a 1 in this bottom right position and then clean up the rest of column 3. So we're 2 steps away. So we're going to move from our current pivot, we're going to move down into the right, and that's going to be the location of our new pivot. So again, the pattern will be to get a 1 and then to get zeros in the rest of column 3. So the way we're going to get a 1 is we're just going to divide our row through by an appropriate number. If we divide row 3 by negative 1, that'll be perfect just to create a 1 for us. So we're going to have 0, 0, 1, and 5. And the top 2 rows are not changing, so we'll just recopy those. And now our final goal is to get zeros in the rest of column 3. So we need to get rid of these 2 1s that are sitting in the other positions. Everything except your pivot should become a 0. So the operation we're going to do is we're going to go current row minus a number times our pivot row, where the number is just whatever number you're trying to turn into a 0. So for the top row, we'd say, well, we're in row 1, and it's a positive 1 that we're trying to get rid of. So we're going to go a minus 1 times our pivot row. Similarly, in row 2, we're going to go row 2 minus our pivot row, and that will work perfectly. So let's try row 1 minus row 3. We're going to have 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. And then 4 minus 5 is a negative 1. Let's try the same thing with row 2 minus row 3. So we're going to have 0 minus 0 is 0. 1 minus 0 is 1. 1 minus 1 is 0, and then 3 minus 5 is a negative 2. And bottom row can just get recopied because nothing's changing there. So we have now successfully created that diagonal form where we've got the 1s along this main diagonal from the top left to the bottom right. We've got 0s everywhere else. And remember, the reason why we like that diagonal form is because we can now read off the solution. Remember, the first column represents x's and then y's and z's. The vertical bar is your equal signs, and then over on the right side, you've got numbers. So if we just read off what the different rows are saying, first row is saying 1 times x. In other words, x is equal to negative 1. Second row is telling us the value of y. Really, it's saying 0x plus 1 times y plus 0z. But if you simplify that, that's really just saying y equals negative 2. And in a similar way, bottom row is saying z equals 5. So you can leave your answer like that, or sometimes we'll write it as an ordered triple, just because it's a little bit faster. X, y, z, negative 1, negative 2, 5. So that's the unique combination of x, y, and z values that solves the original system. So let's try one more problem just to get a hang of this Gauss-Jordan elimination process. So first thing we're going to do is just write up our system in matrix form. So we've got our x, y, z columns. The vertical bar represents our equal signs, and then we'll put in the numbers on the right side here. And we're just going to pull the coefficients out of the system. So 1, negative 3, 4, and 1. 4, negative 10, 10, and then 4. Negative 3, 9, negative 5, and then a negative 6. So that's the matrix form of our system. Now let's think about what we're trying to accomplish here. We're trying to get a 1, otherwise known as the pivot, in the upper left. And that's actually already done for us. So happily, the numbers are just working out nicely in this problem. Once you've got your pivot, then you want to get zeros in the rest of that column. So we're going to get zeros in the rest of column 1. And the operation that you do to create zeros is you go current row minus an appropriate number times your pivot row, where the appropriate number is just whatever number you're trying to get rid of. So let's look at the 4 that we're trying to get rid of. That's in row 2. And we're going to go minus 4 times our pivot row. We're also at the same time going to get rid of that negative 3. So that's in row 3. Remember, you're doing a sign change of the number that you're trying to get rid of. So that's going to become a plus 3 times the pivot row. And those will just be the perfect operations to create zeros in these two positions. So let's work out all the numbers. The top row is not changing, so we'll just recopy that. Then we're going to go row 2 minus 4, row 1. So looking back to our previous matrix, 4 minus 4 is 0. Negative 10 plus 12 would be a 2. 10 minus 16 would be a negative 6. And then 4 minus 4 gives us 0. So you're always just looking back at the previous matrix to figure out the numbers. Last operation that we're going to do, row 3 plus 3, row 1. So let's look back at the previous matrix. So we're going this number plus 3 times that number. Negative 3 plus 3 is a 0. 9 minus 9 gives us a 0. Negative 5 plus 12 gives us 7. And then negative 6 plus 3 gives us a negative 3. So thinking where we're at so far, we created our pivot and we got zeros in the rest of that column. So now we're going to move down and to the right, and we want this guy here to be our pivot for the next step. So our goal is to get a 1 in that position. And the way you get a 1 is just by dividing your row through by an appropriate number. So let's take row 2 and divide it by 2. That will create the 1 for us. So we'll have 0, 1, negative 3, and 0. And I'll just recopy the other two rows at this point. You can keep that pivot circled. I like to circle the pivot just because it helps to figure out what operation to do in the next step. So now what we're trying to do is get zeros in the rest of column 2. So it's really just this -3 here that we want to turn into a 0. So we're going to go current row, do a sign change of the number, +3 times our pivot row. So the pattern we're following for getting that 0 is current row minus the number times the pivot row. So there's always this sign change where if it's a -3 you're trying to get rid of, you're going to go +3 times your pivot row. All right, so let's try this. Row 1 plus 3 row 2 is going to give us 1, 0. In this position here, we're going to be going 4 minus 9 is a -5. And then 1 plus 0 is 1. So that's what we're getting for our top row there. And the other 2 rows are not changing. So pivot row is not changing and the bottom row is not changing because we've already got a 0 in that position. So no work required there. So at this point, the second column is now cleaned up and we're going to go ahead and work on the third column. So we've got 2 more steps to go. We need to get a 1 and then we need to get zeros in the other positions. So we're going to move from our current pivot, we're going to move down and to the right, and this guy here is going to be our pivot for the next step. Okay, so let's write down what we're doing. We're going to get a 1, and the way we're going to get a 1 is take that row and just divide through by whatever number is in that position. So row 3/7 will be perfect to create a 1 in this bottom right-hand corner. So we'll have 0, 0, 1, and then -3/7. We'll just recopy our top 2 rows here. Nothing's changing there. And we can circle our pivot just to help us figure out our last step. So very last step that we need to do here, we're just going to get zeros in the rest of column 3. And that means we're going to have to get rid of the -5 and also the -3. So let's think about what operations are going to get that done. We'll follow the pattern current row minus the number that you're trying to get rid of times your pivot row. That's always the correct operation to create a 0. And so let's think about this -5 that we're seeing in the top right there. That is in row 1. We're going to sign change the number. So row 1 plus 5 times our pivot row. Our pivot is in row 3. And then to get rid of this -3 here, following that same pattern, that's in row 2. We're going to sign change the number. So row 2 plus 3 times our pivot row. Bottom row is not changing, so if you like, you can just recopy that. So let's figure out our numbers just by looking back at our previous matrix. We'll do this one first. Row 1 plus 5 row 3. So we'll go 1 plus 0 is 1. 0 plus 0, 0. And then -5 plus 5 is 0. Okay, over on the right side, we get into a little bit of tricky algebra, so I'm going to do some scribbling on the side here. So what we're supposed to do is 1 plus 5 times whatever is in row 3. So let's just figure out how many sevenths that is. If we multiply 1 by 7/7, it's like 7/7 minus 15/7. That's -8/7. All right, and then very last step, we're going to do, let's highlight the operation that we're doing here. We're going to do row 2 plus 3 row 3. So let's look back at our previous numbers. We're going to go 0 plus 0 is 0. 1 plus 0 is 1. -3 plus 3 is going to give us 0. And then over here, we might want to do just a little bit of algebra on the side. So we're going to go 0 plus 3 times whatever we have in row 3, -9/7. So that's our value there. And we are done the matrix part of the problem because we've created this nice diagonal form where we've got ones along the main diagonal and zeros everywhere else. And that means we're ready to just write down our answer. So it might be helpful to remember what the columns represent here. You got the X, Y, and Z columns. The vertical bars, your equal signs. And then you got your numbers over on the right side. So if we just read off the solution here, top row says X is equal to -8/7, Y is equal to -9/7, and Z is equal to -3/7. So you can leave your answer like that, or if you prefer, you can write an ordered triple, where you go X, Y, Z equals, and then just fill in your values that way. So that's another example of Gauss-Jordan elimination done. So we're going to finish off with a simple real-world problem so that you can start to visualize how systems of equations could actually come into play in everyday work life. So let's imagine that each hat takes 3 hours to produce and it costs $2 to produce. Each coat takes 6 hours to produce and it costs $8 to produce. Let's say that your company has 30 hours available and $32 available each day. The question is, how many hats and coats should you produce, or could you produce? So first thing we're going to need is some variables here. What we're trying to figure out is how many hats and how many coats. So let's let X and Y represent the number of hats and the number of coats. So let's see if we can build some equations here. There's going to be an equation coming from hours, and there's going to be an equation coming from dollars. So we know that each hat takes 3 hours to produce. So that's 3 hours times the number of hats that we produce. And each coat takes 6 hours. So that's 6 times the number of coats that we produce. And if we add those up, that's the total number of hours. We know that our company has 30 hours available each day. So we're going to say that's equal to 30. If we think about dollars, well, each hat costs $2. So we're going to go 2 times the number of hats. Plus, we're going to add on the cost for the coats. Each coat, we said, costs $8. So 8 times the number of coats gives us the dollars just coming from coats. If we add those up, that's our total number of dollars. And we're told that our company has $32. So that's where our second equation comes from. We're really just asking what combination of X and Y values will work. So if we think geometrically, each of these equations represents a line. So we basically have these 2 lines. We're really just trying to figure out, where do these lines intersect? That's going to give us the solution to the system. So that's what we're trying to figure out. Now, the good news here is that we don't have to do too much algebra, because if you look back to the first problem that we did, this is actually the first system that we solved at the beginning of this video. So I could just write ... do a little bit of work, and you can figure out the solution. We found in that problem that the combination was X = 4 and Y = 3. I'll just say see example 1 for all the details at the beginning of the video. So that tells us, we should produce 4 hats and 3 coats. So there's sort of a real world problem showing why we might care about solving systems of equations. So that's our video on systems of equations with unique solutions. Thanks for watching.